Welcome back once again to our course in ENSC 107. This is topic number 11, and we'll be discussing open channel flows. When we say open channel flow, it is a flow of liquid in a conduit. And when we say conduit, for example, pipes, although not necessarily totally enclosed, but another example is, let's say, an open canals. So that's a type of flow wherein the liquid in a conduit in which the upper surface of the liquid is in contact with the atmosphere, or the pressure at that um, at that at that top surface is exposed to atmospheric pressure. And if we compare this, or let me draw it first right here. So let's say here's my conduit, and that's an open canal. This the top surface right here is exposed to atmospheric pressure. But if we compare this to the internal flows that we discussed earlier, when you say internal flows, let's consider an enclosed conduit, or a pipe. So this one, let's say this is internal flows, and this one, let's say this is open channels. So again, when we say open channels, there must be a free surface or a top surface exposed to the atmospheric pressure. So for internal flows, the liquid must be totally filled, or must totally fill this pipe cross section, whereas for open channels, then it can be something like this. So it's just partially filled, and take note that there must be a free surface wherein that free surface is exposed to the atmospheric pressure. So if this is the case, then that's what we call an open channel. But if this is the case, if it is totally filled, then that's internal flows. Now the driving force for internal force, because the fluid is totally filled, then in order for the fluid to flow from one point to another, there must be a pressure, or a pressure difference from, let's say, point 1 to point 2. So there must be a pressure difference in order for the liquid to flow. And let's write here P sub 2 is greater than P sub 1. So right here, because there is a pressure exerted to the fluid, then there's no other way where the fluid can go. So it cannot go in the radial direction, because this is a rigid boundaries, and therefore the flow of motion would be along this. But for open channels, since it is exposed to atmospheric pressure, then the main driving force is actually the gravitational force. Alright, so that's the main difference between internal flows and open channels. So going to our lecture handouts, we have here in figure 11-3. So channels may be constructed in a variety of cross-sectional shapes, and this includes pipe, for example, in this figure, or it can be a closed conduit in a rectangular shape, or an open conduit like this, a trapezoidal canal, or this one. So again, the main distinction for open channel is that there must be a free surface wherein the pressure at that free surface is an atmospheric pressure. So now let's talk about flow classification. We already mentioned this, or we already discussed the classification of flow in terms of uniformity and steadiness. And when we say uniformity, recall that this relates to space, and steadiness, this relates to time. And recall that a steady flow is a type of flow where the properties um, do not change with time. So therefore, when we say properties, let's say we have a discharge properties or a velocity of the fluid, then that means that the properties does not change with time. Whereas when we say uniform flow, that means that in this space right here, let's say the boundary is actually uniform anywhere, any points along this, anywhere along this space or this cross section. All right, so that's it. And it says here in our lecture handouts that in an open channel, usually the parameters that we are interested in are the flow rate, so that's the Q, the velocity, the mean velocity V, so how fast is that liquid is moving, and the depth Y. And when I say depth Y, that's the distance from the bottom surface to the top surface. So that's it. Okay, so steady flow, we can have here three figures, and let's say we have this flow depth at section 1 and another flow depth at section 2. So let's say at an instant of time, then if this remains after, let's say I took a picture at some time, and then after 5 seconds, then, or let's say after 30 seconds, I take another picture, and if I see the same flow depth, then that means that the properties, the flow depth and the velocities, did not change with time. Okay, so we can, if that's the case, then we can call it as a steady flow. But in reality, then we can actually classify, or we can have a combination of steady flow or a uniform flow. So right here in table 11, we can it's already tabulated here. So we can have a steady uniform flow, we can have a steady non-uniform flow, or unsteady and uniform flow, or unsteady and non-uniform flow. So just take note again that when we say uniform, we are referring um, to space, and specifically that means that the parameters or the flow parameters does not change with the space. And when I say steady, the parameters or the flow parameters does not change with time. Now in actual situation, um, we can actually have classifications by, what does it say here, by regions of I mean, we can have terms like, for example, rapidly varying flow. So that means that there's an abrupt changes from the word rapidly. And we can also have gradually varying flow, so that means that um, I mean, the change is gradual. And we can also have a uniform flow depth profile. So right here, when we think about gradually varying flow or rapidly varying flow and the uniform flow depth, let's think about the depth, the flow depth. And recall, when I say flow depth, that's the vertical distance measured from the bed slope, or I mean, bed slope, sorry, but from the bed bottom to the free surface on top. Right, so right here in this scenario, we can actually see the different types of flow. We can have a uniform flow along this, wherein the depth right here at this section is the same as the depth at this cross section. So that means that it is we can say that it's a uniform flow depth profiles. And when I say rapidly varying flow, then there's a rapid change between the flow depth. And when I say gradual, then that means that there's a gradual change in the flow depth. Okay, what else? Then let's talk about the Reynolds number. So the Reynolds number is we can classify. I mean, recall that in our topics in internal flows, that we use the Reynolds number to classify the flow, if it's a laminar flow, or if it's a turbulent flow, or if the flow regime is in the transition region. So when solving, it says here that when solving the Reynolds number, the characteristic length is the hydraulic radius. So for now, let's just keep this at the back of our head. There is a term, hydraulic radius, wherein it refers to the area divided by the wetted perimeter. So if here's our channel or our conduit, and let's say here's our free surface, when we say hydraulic radius, that's the cross-sectional area, that's the A, divided by the wetted wetted perimeter. So wetted perimeter, that means that's the perimeter where the liquid is in contact with the solid boundaries. So that means this length, let's say this length, that that length, and then this one. So that's the area divided by the wetted perimeter. Area is meter squared, this one is meter, therefore the unit of the hydraulic radius is meter. Now recall also that when we say characteristic length, it refers to the geometry of the surface. If it I mean, for example, for a pipe, the characteristic length is the diameter. For a flat plate, then the characteristic length is the length. So it actually depends upon the geometry. So for this open channel flows, the characteristic length is the area divided by the wetted perimeter, and that's our hydraulic radius. Okay, so how do we know if the flow is laminar or turbulent? Then here's our critical Reynolds number. So this is if the flow is or if the Reynolds number is less than or equal to 500, then that's laminar. If it is greater than 2000, then that's turbulent. So recall also that our Reynolds number for open channel flows, that's different from the Reynolds number for internal flows. Okay, another one classification is, classification of open channel flow is based on this dimensionless number. Another dimensionless number called the the Froude number. And when I say Froude number, that's it's just basically another way of classification for open channel flow. But actually, this is more commonly used than the Reynolds number when we're talking about open channel flows. And the idea of Froude number is that it's the ratio of the flow velocity and the surface wave speed. So for example, here's our cross section, and let's say here's our canal, right? And here's our fluid. So we are trying to compare what's the of course at the top there will be wave speed. So we are just trying to compare the speed at the surface and the speed of the flow, because it is possible that that the surface speed is greater the than the speed of the flow, within this flow depth. Or sometimes it's the flow depth is more or has more speed as compared to the surface speed, or probably they are the same. So that is related to the Froude number. In terms of mathematical terms, this Froude number is expressed as the V, that's the velocity of the flow, divided by the square root of G times this times this hydraulic depth. All right, so that's the hydraulic depth, and this is letter C, and that's what we call, I think that's the celerity. Okay, so we can have this classification. Let's say the Froude number is less than 1. What that means, it is classified as subcritical, and if it's greater than 1, it's what we call supercritical, and if it is equal to 1, then that's critical. Right, so what that means is that when I say subcritical, basically we can have, basically that means that the surface wave speed is greater than the flow velocity. Right, so for example, here's our speed, and here's our speed at the bottom. Right. Right, so the speed across the flow is this one. Let's say that vector, and this one is the speed at the surface. So if the speed at the surface is greater than this one, then that means that we have a a number that's less than 1, or a fraction. All right, so that characteristics or the description of that flow is it has slow moving, because this one is slow, and waves can travel upstream against against the current, and also we have this higher depth. Now for critical, I mean supercritical flow, then that means that the speed across the flow depth is greater than the speed at the top, right? So if this is greater, right, this one is greater than this one, so we have a number greater than 1. So the characteristic is, if this is faster, the flow depth, then we have a shallow depth. Usually we have a shallow depth. This one we have a deeper depth, right? So that's for flow number. Then now let's move on to our mean, I mean our next subtopic, which is the mean velocity. Okay, so if here's our cross section, here's our open channel profile or cross section, and here's our fluid profile. So we have in lines here, something like a contour lines, and that lines represents a constant velocity lines. What that means is that the velocity at every point, they're not actually the same, but they're only the same along these lines. Okay, so that's why it's not actually uniform. It's not a uniform profile. So if we try to draw the velocity distribution, for example, here's our open channel, and if we want to check the velocity here, right? So we have something like this velocity, and of course, since this is three-dimensional, then there's gonna be difference as well, because at the solid boundary, or at that boundaries, there is an assumption of the no slip condition. So the velocity at that point is 0, and because of viscous effects and all that, and the maximum velocity is at the center. Now let's try to project it in this view, right? Let's say here's xy, and now this is now our xy. So that means if this is the free surface, here's the free surface, then the velocity profile would look something like this. So take note that this is a solid boundary, and that means we have a 0 velocity right here. And since there is a boundary here, but it's not a solid boundary, it's actually a free surface, then somehow there's going to be a velocity. But the point where there's a maximum velocity is not actually at the free surface, but rather it's somewhere lower than the free surface. So here's our velocity profile. So what that means is, of course, we are just looking at the two-dimensional x and y. What that means is the maximum velocity does not actually occur at the free surface. It actually occurs lower at some distance from this free surface. Okay, so since we have a non-uniform velocity profile in our analysis, sometimes, of course, it's simpler and it's easier to work with the average velocity profile. That's why sometimes we convert this, or we just solve the average profile, which means that it's gonna look something like this, right? So instead of having this profile, this non-uniform profile, we just simplify it, or just translate it to this type of profile. Okay, so now let's move to the channel geometry. Okay, so here it is, the channel geometry. So before delving into the equations of flow, let's say solving the velocity of the flow, or the dimensions of the open channel, first let's discuss this geometry of the channel. Okay, so here's our channel right here. Here's the cross section, and here's the cross section actually along the longitudinal. Right, so this is the side view, and here's the front view rather. Right, so here's our flow. We have this blue, I mean, color or a shading or a blue shading right here, and that's our fluid. And here's our top surface, and see that symbol that represents the top surface, or the surface where it is exposed to the atmospheric pressure. So here it is in the side view. Now the distance or the width of that top surface, that's what we call B, or sometimes I use the term T. Just take note that that's the distance for the top surface. And the bottom, it has also a um, a length. So we have this bottom width. This one is what we call the top width. Top width. So I mark, or I use the symbol B, but sometimes in my computations I just use T just to indicate top. This one is B. That's our bottom width. That's the bottom width of the channel. And we have here the Y. When we say Y, that's actually the depth of flow, or the flow depth. So that's the distance, that's the vertical distance from the bed to the top surface. So if we try to look at the side view, and of course we have a sloping bed bottom, because it's not actually a straight, it's not on a level ground. There must be some angle so that there must be a flow by gravity. And when I say flow depth, that's the vertical distance. So we have here the Y, the distance from this to that, that's what we call our flow depth. And there is another one, depth, that's measured normal to the bed. So when I say normal, so we have the depth D. That depth D is the measurement that is normal or perpendicular to this channel bed. Okay, so that's it. And what else? We also have the PW. That's the wetted perimeter, or that's the perimeter where where the salt sorry where the fluid or the liquid is in contact with the solid surface. So here it is. Okay, what else? We also have the term hydraulic radius, and when I say hydraulic radius, that's the um, ratio of the cross-sectional area, that's this area, cross-sectional area, to the wetted perimeter. And when I say hydraulic depth, it's the ratio of the cross-sectional area to the top width. So that's A over T, or A over B. And when I say bed slope, that's basically the slope of this bed. So in terms of percentage, this is in terms of percentage. Sometimes this is in terms of meters. Length per length. Let's say how many meter. Let's say it rise. Let's say 100 millimeter per 1,000 meters, for example. So that's it. And now let's talk about the properties of the geometric elements. So we know that it is possible to have many types of conduits for open channels. We have a rectangular cross section, we can have a trapezoidal cross section, we can have a triangular, circular, and actually many other shapes. But for us here, this is just what is listed in our lecture handouts. So we have rectangular, trapezoidal, triangular, and circular. And right here in the table, we have the properties and geometrical elements of selected channel cross sections. Or we have the area, then what's going to be the equations, how to solve that. We have here the wetted perimeter, then how do we solve that, the hydraulic radius, the top width, the hydraulic depth, we have here. So it's more on the geometry problems, right? So again, the Y, that's our flow depth. That's the distance from the bed to the top surface. So the area is just simply the area of the rectangle. That's Y times B. So that's why it's BY. For trapezoid, we can actually derive the equation for that. But for simplicity, it's just actually the area of this plus the area of that and the area of this. And we have here the slope. So take note, this is not the bed slope, but rather this is the side slope. So the slope along the sides, that's 1 over T, or vertical, and this one is horizontal. So it says here for trapezoidal, the area is just simply b plus y times y, b plus y times y. And for this one, triangular, we have this t is this one, the side slope. So just take note of this, that's the horizontal um, value. And for circular, we need this angle. And for wetted perimeter, this is b plus y, so that's why b plus 2y. And for trapezoidal, then we have that. Okay, so I guess anytime we solve for open channel problems, and we might refer to this table. Okay, so now let's move on to the analysis of steady uniform flow. So let's just limit our computations regarding steady and uniform flow. That means that the depth does not change along the length. Okay, so um, we have this term Chezy equation. Basically, when when let's say here's our channel and here's our flow. So when this water is flowing, actually there is a resistance, or there is a viscous effects because of that solid boundaries and also the properties of the fluid. And that's why in our topic in internal flows, we mentioned about the Darcy-Weisbach equation, um, just to take into account the viscous effects, or how to quantify the viscous effects along the internal, in the internal pipe flows. For open channel flows, the equation is, one of the equation is this, the Chezy equation. But we'll just fast forward because what we will use in our computation is this one, the Manning's equation. Okay, so the idea again is, because there is viscous effects, then there must be some coefficients or some parameters that must be included in our computations for um, I mean there must be these coefficients. Let's say the C right here, that's the Chezy um, coefficient, just to take into account the viscous effects, right? So what we want in open channels, or sometimes it's just the velocity. And of course, if we can solve the velocity of the flow, then we can compute uh, for the other parameters. So how do we solve that velocity, and also taking into account the the viscous effects? So we have this equation from Chezy, and it has this coefficient, Chezy coefficient, and we can solve that using this, right? And the equation is this: C is equal to square root of 8g times divided by the friction factor as a function of Reynolds number and the relative roughness, and which can be obtained in our Moody diagram, right? So that's one way, but there's another common equation called the Manning's equation. So take note, Manning's equation, named after this Irish engineer of the 19th century. And there is a C, except that the value of C is different from the Chezy equation. And if we solve this, or if we apply this to this equation, to this proposed equation, and by the way, take note that these equations, they are empirical correlations or empirical equations, which means that they are not derived from something a more from a more fundamental equations, but rather they are from observations or experiments. Okay, so that's our empirical equations for the velocity. So if you substitute that, what we get is this form. So v is equal to 1 all over n, r raised to 2/3 s raised to 1 off. By the way, I think this is not 0.5. This must be, if I'm not mistaken, this should be, or maybe correct, because this is 1 over 6. Okay, anyway, so here it is. This is 2/3, r raised to 2/3, and s raised to 1 half. So now let me write it here. V is equal to 1 all over n, r raised to 2/3, s raised to 1/2. So that's our Manning's equation for the velocity of the flow. So what is this s? When I say s, that's the channel slope or the bed slope. And it is raised to 1/2. This r, this is our hydraulic radius. Hydraulic radius. So that means we have to change this. This is not wetted perimeter, but rather hydraulic radius. And recall that the hydraulic radius R H is equal to the area, cross-sectional area, divided by the wetted perimeter. Right? And this one, this n, that's what we call the Manning's coefficient. Manning's coefficient. Okay, and we also have actually there is a factor here, or another variable that's actually k, because whether if you use it in SI units or US units. So if for SI the k is just 1, for let's write here SI, but for English this is 1.49 for English units. Okay, so this Manning's coefficient, this can be found from the table. Alright, and that's our velocity. Right, so again, I guess we'll continue this lecture in the next video.